what you would see particles in a solid doing. They're just vibrating. And the volume of the solid itself is dependent on the volume of the size of its particles. However, if we shrink this down, put it in a box, the volume is still the same as what we had before. I just shrunk it down. I'm going to seal the box and now heat it up a little so that we now have gas. And what is so important here is that to understand not only that this is what all gases are doing, they're zooming around, and this is extreme slow motion. Gases are actually moving at an average speed of about 1,200 miles per hour. So if you speed this up to 1,200 miles per hour, that would be a more accurate portrayal of the better simulation of gas particles. But if you were to count the amount of collisions on a square inch of gas particles, it would add up to 2 quintillion collisions per square inch every second. That's 2 billion collisions. The significance of this is that it produces a lot of force. So I was telling you that there were 2 quintillion collisions on a square inch of surface, of any surface, per second. The force resulting from those 2 quintillion collisions is equal to 15 pounds. This is a 15-pound weight. And this is 1 square inch. So you can picture the amount of force. If I put this weight on that 1 square inch of surface, that's the amount of force that is hitting any square inch of surface anywhere, including your body. Every square inch of your body has this amount of force pressing on it. And if you can imagine how many square inches you have on your body, it's a tremendous, tremendous force that's just squish you like a bug. But it doesn't. I want you to think about why that is the case, and I'll get back to that. So while you're thinking about that, I'll show you some other things. And one of the things I want to show you is the force of that on something that is a little less substantial than a human body. So I'm going to pour a little bit of water in here. And I'm going to heat it to boiling. Now, there's only one thing more exciting than watching water boil. Yes, you're right, it's watching paint dry. It shouldn't take long to boil because I've been heating it. So hopefully that'll boil quickly. What I'm going to do is I'm going to get some ice water. So what I want you to focus on is the fact that on every square inch of the surface of this can, this very thin tin aluminum can, is 15 pounds of force. Why do you think the can isn't being crushed right now? There's the same exact force on the inside, and so they equal each other out. We can't feel that force at all because they're completely equaled out. So I'm going to have the water boil for a bit, and then I'm going to seal the can by turning it upside down into some cold water. If I let it boil enough, in other words, turn the liquid water into gaseous water, the direction of the gaseous water will continually, since it's rising off the water, will continually be up. What's that going to do to the air inside the can? I'm not sure if I heard the right answer. Anyway, it's just going to push it out. Did somebody get that? Yeah. Okay. We're very good. Whoever said. All right. So it's boiling. I'm going to put. I got to get all the ice I can in there. I should have been. I forgot about this can. Oh, it's a bigger can, you know. Bigger can. The bigger they are, the bigger the. Whatever. Okay. So I'm now going to find my tongs. I found them. I'm going to take the can from the bottom. So I'm not holding it in the middle. I'm going to take it from the bottom, and I'm just going to push it underneath the water to seal the opening. Any guesses on what's going to happen? I heard explosion. I always tell my students, anytime there's an explosion in the room, we always quickly exit the room. Same goes for you. right, you ready?
Yeah.
So I'll pass this around. If you feel it, you can see that there's extremely little space in here. There's almost no space whatsoever. Sam, you get the first to see this again after, what, 13 years, the last time I showed you? Can anybody want to try to explain why that crushed?
Magic.
Yes.
Because of the heat, all of the air inside of the bottle kind of just went off all at once, so there's nothing in there keeping it open, so it just closed.
So you were right 95%. The 5% you're missing was there was something keeping it from crushing, which was water vapor, which is also gas. But what happens to the water vapor when I cool it down? And so it's no longer a gas. So you no longer have anything in there, which is exactly what you were saying. And so you have that 15 pounds just crushing it. Jim?
Professor, why didn't it suck the cold water up into the can?
Gravity. And well, really, I mean, there's just so much more force on the outside before that could ever happen. So I thought I'd bring a. I never did a can this big. That's why I did the little can first. So that gives you an idea of, you know, the 15 pounds. The idea of 15 pounds pressing on every square inch of a surface. And this is just something very, very quick. For example, it's a syringe that's closed at one end, and if I pull it out, it just goes right back. Can anybody explain that? Yes?
It's a vacuum, and vacuums fill themselves.
Well, it is vacuum, but what this is maybe about a square inch. Is there any force pushing on this?
Oh, yes.
How much force? 15 pounds. Constantly pushing, so it pushes it right back in. So there's so many things that you can do to see this 15 pounds that we never really think about. And next thing is, what does it mean for pressure to go the other direction? So this is about explosions, and so I'm taking a cue from the last song. Wasn't there something about explosions in there? Yeah. Okay. So the explosion will be contained. You don't have to worry about it. But should we do the big can? Yeah. All right. And again, you can feel there's just very little space in there. So you can pass that around. All right, so in order to make my little explosion, I need a source of energy. Explosions are simply gases that are extremely rapidly formed in a chemical reaction at a very high speed, and so they're pushing out. And what I'm going to do is put a little alcohol in here. So just a vial of alcohol. I'm just putting a little bit. You can see it's not much. And I'm going to shake it. What I'm going to do is, there are two nails sticking out, and there's a gap between them. If I put electricity through the nails, the electricity will arc from one nail to the other. And I'll show you that. This is a Tesla coil, and it generates electrons at the tip. There's a very large potential energy difference, if you know what that means, between the tip and the air. The potential energy is relieved by the release of electrons. If that meant anything to you, great. If not, I can explain more later. So this is what I mean by electrons. So the electrons are arcing toward a very conductive surface. You don't see the electrons, you see the air that it is energized, the electrons are energizing. So that light is the air that is being energized and releasing light. Okay, I'm now going to bring it up to the nail. All right, you ready? Oh, I forgot something. Okay, here we go. And okay, back to the last thing is
It just keeps getting out like bigger things.
Does anybody come up with why we are not getting completely crushed and squished by 15 pounds on every square inch of our body? Yes, that's one, absolutely right, but there's also a more sophisticated explanation. Yes?
Like, even paper, if you push from the same amount of force on both sides, it's not going to catch you.
That is so beautiful. That you should already be in chemistry. So what is pushing against the air that's pushing on us? Our bodies are pushing out at 15 pounds per square inch. To prove this to you, everybody's done this. If you So what a vacuum cleaner does, it takes the air, the motor is simply designed to take the air out of the hose. Air is already going at 1,200 miles per hour. So where's the air going to go if we take the air out of the hose? It's already traveling 1,200 miles an hour, it's going to go right into the hose. This is how we breathe. You open up your lungs, the air goes in. If you open up your lungs faster, did you make the air go faster? No, it's already moving at 1,200 miles per hour. You just opened up your lungs faster, that's all. So when you do this, you feel your skin going into the hose, right? Does everybody agree with me? You feel your skin going into the hose. There's nothing in the hose pulling on your skin. Why would your skin go into the hose? The pressure, you are pushing out at 15 pounds per square inch. When there's nothing to push out against, it's just going to keep going out until those very strong bonds between atoms, the very strong attachments of cells by those very powerful and strong fibrous proteins will hold your skin together. And so it only comes out a little bit. I'm sure you've all wondered, when you pull your skin, why doesn't it just come off my body? This is something that people must have wondered. The reason is because of the very strong bonds between atoms and molecules and attachments of cells to each other. Are there any questions? That's it.